Okay, so picture this scene. It's August 2020. You're standing on the deck of the USS Mustin. It's an Arleigh Burke-class destroyer, which means you are standing on about 9,600 tons of American steel.
Right.
And you're cutting through the choppy waters of the Taiwan Strait. To your port side, you see the coast of mainland China. To starboard, the jagged mountains of Taiwan.
It's arguably the most tense stretch of water on the entire planet.
It really is. And if you look at that ship, it just screams old school military power. It's got thick armor, big guns, missile tubes. It looks like a floating fortress.
Sure.
But the argument we're going to unpack today is that the most dangerous thing on that ship, it isn't the explosives, it isn't the steel, it's the silicon.
Right. It's the thousands of microchips that are processing the radar data, guiding the missiles, linking the captain to the Pentagon. If you take those chips out, that billion-dollar destroyer is basically just a floating scrap heap. It can't see, it can't shoot, it can't move.
Today we are doing a deep dive into Chip War by Chris Miller. And the core mission here is to understand how this tiny wafer of silicon something you can fit on your fingertip became the new oil. And this isn't just about why your iPhone is fast.
No.
This is about the single resource that now defines military power, economic survival, and, the geopolitical fate of the entire world.
And that comparison to oil is really the key insight to start with. For the last century, geopolitics was sort of defined by something called the Malacca Dilemma.
That's the fear that an adversary could block the Strait of Malacca, right? Cut off the oil supply to East Asia.
Exactly. You cut the oil, the tanks stop running, the factories go dark.
Yeah.
But Miller's argument is that we've moved past that. Beijing and Washington aren't just worried about barrels of oil anymore. They're terrified of a blockade measured in bytes.
A blockade measured in bytes. I love that line.
It's the reality. If you cut the flow of chips, the economy stops running. Not just the gas stations, but the data centers, the banks, the hospitals, everything.
So to understand how we got to this point, where the entire world is hanging by a thread of silicon, we have to go back. And the history, surprisingly, it starts with the exact opposite of high-tech. It starts with what Japanese soldiers called the Typhoon of Steel.
That's World War II. And Typhoon of Steel was the phrase they used for the American bombardment. They were just completely overwhelmed. The U.S. won that war through sheer industrial attrition. We poured more steel, more aluminum, more explosives onto the battlefield than anyone else could match.
And the book points out there were two young men watching this happen, right? Akio Morita in Japan and Morris Chang in China. They saw firsthand that, material superiority wins wars.
They did. But the U.S. military saw something else. They realized that throwing steel has a ceiling. You can't just keep building bigger and bigger bombs forever. Eventually, you hit diminishing returns. They needed better aim. They needed calculation.
Which brings us to, let's call it, the prehistoric era of computing. We're talking about the ENIAC.
The ENIAC. It was a monster. It had 18,000 vacuum tubes. It took up an entire room. And the problem wasn't just the size, it was reliability. Those vacuum tubes were like light bulbs. They burned out constantly.
And didn't it attract, actual bugs?
It did. Moths would fly into the glowing tubes, get fried, and short them out. That's actually where we get the term debugging.
Yeah.
You literally had to sweep dead moths out of the machine.
Which is a funny image, but it highlights a really serious military problem. You can't put a room-sized computer inside the nose cone of a missile.
No.
Especially one that breaks every 2 days because of insects.
Exactly. The world needed a switch that was solid, small, and didn't attract moths. And that is the transistor. And the story of the transistor brings us to the villain of early Silicon Valley, William Shockley.
The father of the transistor. But by all accounts, not a great dad.
A brilliant physicist at Bell Labs, a Nobel Prize winner, but an absolute nightmare to work for. He was out to California to start Shockley Semiconductor, hires the brightest minds in the country. But he's so paranoid, so abusive, so controlling, that his 8 best engineers quit en masse.
The traitorous 8.
Right. They walk out, they get funding, and they launch Fairchild Semiconductor. And I want to pause here because this moment is so crucial. It didn't just create a new company. It created the whole culture of Silicon Valley.
You mean the idea that your loyalty to a company is, secondary to the innovation itself?
Exactly. The idea of equity, of startups, of leaving your boss to start a competitor, of rapid iteration, that all starts with the rebellion against Shockley. If they'd stayed and been obedient corporate guys, Silicon Valley as we know it might not even exist.
And out of that rebellion comes the big bang of our story, the integrated circuit.
It happened almost at the same time in two places. You had Jack Kilby at Texas Instruments and Bob Noyce at Fairchild. Before this, engineers were soldering individual transistors together by hand. It was slow, it was expensive, it was fragile.
The tyranny of numbers. The more complex the circuit gets, the more likely it is that one of those solder joints would fail.
Precisely. Noyce and Kilby figured out how to print the entire circuit transistors, resistors, capacitors, everything onto a single slab of semiconductor material. No wires, no soldering, just one solid block.
Okay, so they have this miracle chip. It works, but here's the catch, and I think people forget this. It was astronomically expensive.
It cost more than a car.
Right. So in a normal free market, this technology should have died. No one's going to buy a radio that costs $10,000. So how did the industry survive? Who bought them?
And this is where the narrative really flips. We like to think of tech as this great triumph of free market capitalism. But the reality is, the first customer, the only customer that mattered for years, was the U.S. government.
It was the Cold War.
It was Sputnik. The Soviets launched the first satellite in 1957. Panic sets in. NASA is formed. They need to get to the moon, and they need a guidance computer that's light enough to actually fly. You can't send vacuum tubes to the moon.
So the Apollo program basically became the R&D budget for the entire chip industry.
Apollo and the Minuteman second missile. The Air Force needed thousands and thousands of chips to guide nuclear missiles. They bought so many that they drove the price down from, around $120 a chip to $15 in just a few years.
That is a massive subsidy.
It is. The U.S. military effectively bought down the cost curve for the whole industry, which made it cheap enough for civilians to eventually have, pocket calculators and then PCs.
And it's that volume that unlocks Moore's law, the prediction that computing power would double every 2 years. But to keep up that pace, they had to figure out how to make the transistors smaller and smaller. This is where we get into the dark arts of manufacturing.
Photolithography. This is the technical leap that really defines the industry.
And the book tells the story of J. Lathrop. He basically just turned a microscope upside down.
That's the simplest way to picture it,
Yeah.
Think about a regular microscope. You look through a lens to make a small thing look big. Lathrop realized if you reverse the process, you can shine light through a lens to make a big pattern look tiny.
It's like stenciling with light.
Precisely.
Yeah.
You create a mask, which is just like a stencil of the circuit, and you blast light through it onto the silicon wafer. And that lets you print millions and eventually billions of transistors onto a chip the size of your fingernail.
But once you can print them, you have to assemble them. And this is what sparked the first wave of globalization. And Miller makes this point so strongly. Globalization didn't start in the 90s. In the chip world, it started in the 60s.
With a guy named Charlie Spork, the operations genius at Fairchild. He was obsessed with cutting costs. He realized that assembly, packaging the chips, putting legs on them, that was labor intensive. So he looked to Asia.
Hong Kong, Singapore, Malaysia.
The transistor girls. They set up these factories where labor was just pennies on the dollar compared to California. But here's the twist. It wasn't just about cheap labor. Spork started to realize that the chips coming out of Asia were actually better.
Better.
The yield was higher. The workforce was more disciplined, more precise. In the U.S., you had a bit of a cowboy culture, people taking smoke breaks, not following the exact protocol. In Asia, the attention to detail was obsessive. And this is what laid the roots for the supply chain that we have today.
And this brings Morris Chang back into the picture. The kid who watched the bombs fall in China is now working at Texas Instruments.
And he's a production wizard. He was taking these production lines that were failing and boosting their yields to 25–30%. He was building this deep institutional knowledge of how to manufacture in Asia. Keep his name in your head because he is going to become maybe the most important man in the semiconductor world later on.
So while the U.S. is building this global network, what's the Soviet Union doing? They have excellent physicists, they have rockets. Why didn't they have a Silicon Valley?
They tried. They built a whole city called Zelenograd, literally Green City, and they modeled it on American suburbs. But they made a fatal strategic error. They decided copy.
The copy it strategy.
Yeah, Minister Shokin, who ran their electronics industry, basically ordered his spies to steal American designs and just clone them.
There's that incredible story about the fishermen off the U.S. coast.
Right. They haul up a Soviet spy buoy, they crack it open, and inside they find perfect replicas of Texas Instruments chips, down to the finest detail.
Okay, so devil's advocate here. If they could copy them so perfectly, why did they lose? Why didn't that work?
It's because of the cake metaphor. If I steal a cake from a famous bakery, I have the final product. I can taste it, I can measure it, but I don't have the recipe. I don't know the exact oven temperature, the humidity, the specific brand of flour, or the timing.
And in chip manufacturing, those variables are everything.
It's more art than science sometimes. The Soviets could copy the design, the layout, but they couldn't copy the process. Their yields were terrible because they didn't know the recipe. And by the time they finally managed to clone an Intel chip, Intel had already released the next generation. They were permanently freezing themselves 5 years in the past.
Plus, the U.S. knew they were stealing.
The Farewell Dossier. A KGB agent named Vladimir Vetrov handed thousands of documents to the French, exposing the whole operation. The U.S. used that intelligence to feed the Soviets bad designs chips that would work for a while and then just fail. It drove them crazy.
So the Soviets basically defeat themselves by trying to be a copycat. But then, in the 1980s, a real challenger shows up, one that isn't stealing but innovating: Japan.
This is the era of Akio Morita and Sony. Japan pivoted from making cheap knockoffs to making these high-quality electronics. The Walkman, the Trinitron TV. But the real battleground was memory chips DRAM.
And this is where the U.S. got complacent. American companies thought they owned the market. They invented it, you know?
Until Hewlett-Packard did a blind test. A guy named Richard Anderson at HP tested American memory chips against Japanese ones. And the results were shocking. The Japanese chips had a failure rate of 0.02%. The American chips failed 10 times as often.
10 times the failure rate. That's not a rounding error. That is a humiliation.
It was. Japan had mastered the manufacturing process in a way Silicon Valley just hadn't. They were treating it like a precise industrial art, while American firms were more focused on design and, moving fast.
And the consequences were brutal. Intel, National Semiconductor, they were bleeding cash. There was a genuine fear that Silicon Valley could turn into a Rust Belt.
And that economic fear turned into geopolitical panic. You had this famous book come out, The Japan That Can Say No, and a Japanese politician in it argued that Japan actually held the balance of power in the Cold War.
The argument was that U.S. missiles relied on Japanese chips, wasn't it?
Exactly. He said, if we sell these chips to the Soviets instead of you guys, the global balance of power shifts overnight. Washington was terrified.
So how did the U.S. fight back? Because, obviously we're not speaking Japanese in Silicon Valley today.
It required a ruthless pivot. And the central figure here is Andy Grove at Intel. His motto was, only the paranoid survive.
Great book title.
Grove looked at the numbers and just realized Intel could not win the memory war. The Japanese were too good, too cheap. So he did something that was, at the time, unthinkable. He walked away from the memory business, the business Intel was built on, and he bet the entire company on microprocessors, the brains of the computer.
Which turned out to be the right bet. But we still needed memory chips. We couldn't just surrender that entire industry to a geopolitical rival.
Enter the potato king.
I love this guy. Jack Simplot.
An Idaho billionaire. Made his fortune inventing the frozen French fry and supplying McDonald's. He didn't know a thing about physics, but he knew about commodities.
And memory chips are commodities.
Exactly. He realized memory chips were just like potatoes. They're uniform, they're interchangeable, and the lowest price wins. So he funded this tiny startup in Boise called Micron. And they survived by being ruthlessly cheap, scrappy, and efficient.
But there was also a geopolitical play here, wasn't there? The U.S. government didn't just sit back.
No. They followed the logic of my enemy's enemy is my friend. Japan was the economic enemy at that moment. So the U.S. and Silicon Valley quietly started to aid South Korea.
Samsung.
Lee Byung-chul, the founder of Samsung, wanted to get into chips, and the Americans were more than happy to help him if it meant undercutting the Japanese. They transferred technology, provided training, and helped Samsung become the giant it is today. It was a checkmate move against Japan.
That is just a fascinating piece of history, that we built up one Asian giant to take down another. But while all this corporate shuffling is happening, the U.S. military is undergoing a transformation that brings us to the modern era, the offset strategy.
This was the brainchild of William Perry at the Pentagon. He looked at the Soviet Union in the 70s and realized, we will never match them tank for tank. The Soviets could just build more.
So quality over quantity?
Precisely. Perry realized that if you put a microprocessor in a missile, you don't need to fire 1,000 rounds to destroy a bridge. You just need one.
The book contrasts this with Vietnam.
In Vietnam, the U.S. dropped thousands of dumb bombs on the Phan Hoa Bridge and barely even scratched it. It was a complete waste of steel.
Fast forward to the Gulf War in 1991.
The whole world watched on CNN as a laser-guided bomb flew down a ventilation shaft. It was shocking. And that was the moment the Soviet generals and the Chinese generals realized the game had completely changed. Silicon dominance meant military dominance.
But this reliance on silicon led to a new vulnerability. We wanted the best chips, the fastest chips, and that demand for perfection led to this extreme specialization in the supply chain. And this is where the U.S. actually lost a major battle. The tools.
This is the part of the story that should really worry us. To make these advanced chips, you need that lithography machine we talked about, the stenciling with light machine. But modern ones are incredibly complex, and the U.S. used to lead this. A company called GCA invented the step-and-repeat camera. They were the kings.
That's what happened?
Wall Street happened. GCA was run by finance guys, not engineers. They prioritized the stock price over R&D. They let quality slip. They treated their customers poorly.
And Nikon and Canon just ate their lunch.
And eventually, a Dutch company called ASML took over everything. So now, the machine you need for the most cutting-edge chips, extreme ultraviolet lithography, or EUV, is made by one company, ASML.
One company in the Netherlands.
Yes, an EUV machine costs $150 million. It involves firing a laser at a tiny droplet of tin that's moving through a vacuum at hundreds of miles per hour to create plasma. It is the most complex machine humans have ever built. And the U.S. can't make one. China can't make one. Only the Dutch.
And where do those machines go?
They go to Taiwan, to TSMC, the company founded by our guy, Morris Chang. Today, TSMC manufactures 90% of the world's most advanced processor chips.
90%? That's not a supply chain, that's a bottleneck.
It is a single point of failure for the entire global economy.
Which brings us right back to the USS Mustin in the Taiwan Strait. We've built a world where everything, our phones, our cars, our stock markets, our missiles, relies on chips made in a few buildings on an island that China claims as its own.
We call it the Silicon Shield. The idea is that Taiwan is so critical to the world economy that the U.S. has to defend it, and China can't afford to destroy it.
It's mutually assured economic destruction.
That's the hope. But, hopes aren't a strategy. If a war breaks out, or even if a blockade just stops those chips from leaving the island, the estimates are catastrophic. It wouldn't just be a recession, it would be a global depression, instantly. Manufacturing of cars, planes, electronics would just stop.
It really changes how you look at the device in your pocket. It's not just a gadget. It's the survivor of 70 years of spy games, trade wars, and industrial attrition.
And it is the finite resource that will likely determine who wins the 21st century.
So here's the final thought for you to chew on today. We started by saying chips are the new oil. But imagine if all the world's oil refineries were located in one city in one of the most politically unstable regions on Earth. That's the reality of our digital world. We are dazzlingly efficient, but we are terrifyingly fragile. If the fabs in Taiwan go dark tomorrow, what happens to your life?
That is the question that keeps the Pentagon up at night.
Thanks for diving deep with us. We'll see you on the next one.